Every second, the universe unfolds secrets that challenge our understanding of reality. What happens when stars collapse into nothingness, forming black holes that defy the very laws of physics as we know them? These cosmic enigmas not only warp the fabric of space and time, but also hint at the existence of dark matter, a mysterious substance that makes up nearly 85% of our universe, yet remains unseen. Join us as we delve into some of the most terrifying anomalies in the universe. A rogue planet is defined as a celestial body that has been expelled from its original planetary system and now wanders through the galaxy without a host star to orbit. These planets can vary in size and composition, just like those found in established solar systems. But the key distinction is their isolated nature. Research indicates that there could be billions, or even more, rogue planets drifting through the vastness of space, each potentially holding secrets about planetary formation and evolution. The significance of rogue planets lies in their ability to challenge our understanding of how planets are formed and how they interact with their environment. Traditionally, we have believed that planets develop in tandem with their stars, but rogue planets suggest that the process can be much more complex. They may result from gravitational disturbances that eject planets from their systems, which raises questions about the stability and dynamics of celestial mechanics. Furthermore, rogue planets could potentially harbor unique conditions for life. While they are not tethered to a star, they might maintain some internal heat from the formation process or radioactive decay. This could create subsurface oceans beneath ice crusts, akin to what is theorized for moons like Europa and Enceladus. The search for these mysterious bodies expands our quest to understand what types of environments could support life beyond traditional star-centric models. Exploring rogue planets also opens up new avenues in astrophysical research. Their existence challenges scientists to reconsider the mechanisms of planet formation and migration, pushing the boundaries of our knowledge about the universe. As we uncover more about these nomadic worlds, we begin to piece together a more comprehensive picture of the dynamic processes that shape the cosmos. Rogue planets, unlike traditional planets, do not orbit any star. Instead, they wander through the galaxy untethered and adrift, having either been ejected from their original star systems or formed in isolation, far from any stellar influence. While typical planets are part of a star's gravitational pull, circling around often with a predictable pattern, rogue planets exhibit a sense of freedom and mystery as they traverse the cosmos. These solitary wanderers can vary significantly in size and composition, much like their star-orbiting counterparts. Some may be similar to Earth, while others could be massive gas giants featuring thick atmospheres. The lack of a closed star means that these planets do not receive the warmth and light that would typically be abundant in a planetary system, leading to extremely low temperatures on their surfaces. In some intriguing scenarios, certain rogue planets might even retain geothermal heat from their formation, or possess internal processes that could sustain pockets of warmth. Rogue planets also invite scientists to ponder the fundamental nature of planetary formation. They challenge the traditional models that dictate how planets form within the confines of a stellar nursery. The potential existence of these planets suggests that the universe may be populated by vast numbers of these independent worlds, possibly even more than those that remain bound to stars. This expanding understanding offers a fascinating glimpse into the dynamics of planetary systems and highlights the diverse possibilities of cosmic evolution. Moreover, the discovery of rogue planets is not merely theoretical. Astronomers have identified numerous candidates through various observational techniques. These discoveries not only enrich our understanding of planet formation and movement, but also inspire curiosity about the potential for life in places far removed from the central warmth of the sun. The idea that life might exist in the depths of the cosmos, on a planet cut off from stellar influence, opens up thrilling new discussions in the field of astrobiology. Rogue planets are fascinating celestial entities that roam through the universe without being tethered to any star. Evidence of their existence has accumulated over the years through a variety of observational techniques and astrophysical phenomena. One of the most compelling pieces of evidence comes from gravitational microlensing, a method that detects the influence of a planet's gravity on the light from a distant star. When a rogue planet passes in front of a more distant star, it can bend and magnify that star's light, offering astronomers a glimpse of the planet's presence, even without directly observing it. Another significant indication of rogue planets can be found in the dynamics of star systems. Some models of planetary formation suggest that, during the chaotic early stages of a planetary system, particularly in dense clusters, planets can be ejected from their host stars due to gravitational interactions. This occurs frequently in environments like globular clusters, where the proximity of many stars leads to interactions that can set a planet on a path into interstellar space. Studies of young star clusters show that, in certain cases, a surprisingly high percentage of planets could be rogue, which aligns with theoretical predictions. Moreover, observational surveys with powerful telescopes have turned up tantalizing hints of rogue planets. For example, surveys in the infrared spectrum have detected objects that exhibit planet-like characteristics floating freely in the dark reaches of space. These observations suggest that rogue planets are not only theoretical constructs, but may be numerous, existing beyond the reach of any star's light. In addition to these direct and indirect evidences, computer simulations of galaxy formation and dynamics further reinforce the idea of rogue planets. These simulations frequently predict their existence and suggest that they could number in the billions or even trillions throughout the cosmos. With ongoing advancements in telescopic technology and methods, the quest to learn more about rogue planets continues, promising to uncover even more about these mysterious wanderers. Rogue planets, those mysterious bodies drifting through space unbound by any star, open up fascinating possibilities for the development of life in the cosmos. Without a star to warm them, these planets may seem inhospitable at first glance. However, their unique environments could host life, albeit in unconventional forms. For instance, some scientists theorize that subsurface oceans could exist beneath layers of ice kept warm by geothermal heat. Such conditions may create niches where microbial life can thrive, reminiscent of environments found in the frigid depths of Earth's own oceans. Additionally, rogue planets may contribute to the cosmic ballet of life through their gravitational influence. When these planets encounter a star system, they can disrupt the orbits of nearby celestial bodies, including moons and other planets. This disturbance can theoretically create new pathways for life to emerge. For instance, a perturbation could lead to an increase in asteroid collisions that deliver organic materials to a planet or moon, fostering the conditions required for life to begin. In this sense, rogue planets could act as cosmic catalysts in the grand story of life. Furthermore, the study of rogue planets enhances our understanding of habitability. With the identification of these planets and the exploration of their characteristics, scientists are redefining what makes a celestial body capable of supporting life. Factors such as temperature, atmospheric composition, and even chemical diversity are now recognized as crucial in assessing a planet's potential. As we expand our search for life beyond traditional habitable zones, rogue planets can no longer be considered outliers. Instead, they represent a diverse range of possibilities in the ongoing quest to find life among the stars. This exploration encourages us to think critically about life's resilience and adaptability. Much like Earth's extremophiles, organisms that thrive in extreme conditions, life on rogue planets might also adopt unexpected strategies for survival. As we unveil more of these celestial wonders through ongoing astronomical surveys, the universe unfolds new narrative layers, reminding us that life, however fragile, may exist in forms we have yet to imagine. The discovery of rogue planets, those celestial bodies drifting through a galaxy without being tethered to any parent star, has fundamentally shifted our understanding of how planets form and evolve. Traditionally, it was thought that planets developed around stars in a more stable, predictable manner. However, the existence of these wandering worlds suggests that planetary formation can occur in vastly different environments, ones that don't conform to our earlier models. Rogue planets may originate from several scenarios. Some could have formed in the vicinity of a star, only to be ejected due to gravitational interactions with other celestial bodies, perhaps during the chaotic period of a planetary system's development. Others might form in isolation in the interstellar medium, where gas and dust coalesce under gravity's influence, creating planets without the need for a star. This variability implies that our solar system is not the sole template for planetary formation in the cosmos, broadening our understanding of potential planetary architectures. Furthermore, the presence of rogue planets raises intriguing questions about how these planets might interact with other objects in space. Some studies suggest that these planetary nomads can influence the development of other celestial bodies, even from afar, impacting trajectory of comets and asteroids, or perhaps even contributing to the atmospheres of nearby worlds if they pass close enough. The potential for rogue planets to host exotic life forms or possess their own unique ecosystems adds another layer of complexity to this narrative. As we continue to discover more about these elusive worlds, we find ourselves re-examining our existing theories of planetary systems. Each rogue planet discovered challenges scientists to refine their models and consider an expansive array of possibilities, thus enriching our understanding of not just individual planets, but also the intricate tapestry of the universe itself. Black holes are intriguing cosmic entities defined by a few key characteristics that separate them from other astronomical phenomena. At their core lies a point known as a singularity, where the gravitational pull is so intense that matter is infinitely compressed. This singularity is surrounded by an event horizon, which serves as a point of no return. Crossing this boundary means that nothing, not even light, can escape the immense gravitational grip, making black holes invisible to direct observation. Mass is another critical defining trait. Black holes vary significantly in mass, from stellar black holes, which are formed after massive stars exhaust their nuclear fuel, collapsing under their own gravity, to supermassive black holes that reside at the centers of galaxies and can contain millions or even billions of times the mass of our Sun. Intermediate black holes exist as well, though they are less understood, likely formed through merging black holes or the direct collapse of massive stars. Another fascinating characteristic is the way black holes interact with their surroundings. As they pull in surrounding material, such as gas and dust from neighboring stars, this matter forms a swirling disk known as an accretion disk. This disk heats up due to friction and can emit powerful radiation, making black holes detectable indirectly. In addition, black holes can produce jets of high-energy particles that shoot out into space, forming a striking contrast against the dark backdrop of the black hole itself. Lastly, black holes can also exhibit a phenomenon known as gravitational lensing. This occurs when their intense gravitational field bends a path of light from object behind them, creating distorted images or even multiple images of those celestial bodies. This characteristic not only evidences the extraordinary effects of gravity at play, but also aids astronomers in identifying black holes throughout the cosmos. A black hole is formed from the remnants of a massive star that has reached the end of its life cycle. When such a star exhausts its nuclear fuel, it can no longer support itself against the pull of its own gravity. As the star's core collapses, it creates an incredibly dense and hot environment. If the original mass of the star is enough, typically more than 20 times the mass of our Sun, the collapse becomes so intense that it pushes the limits of our understanding of physics. During this collapse, the outer layers of the star may explode in a spectacular event known as a supernova. This catastrophic explosion occurs when the core implodes and then rebounds, scattering the outer layers into space, enriching the cosmos with heavier elements formed within the star. What remains is a core so dense that it creates a gravitational field from which not even light can escape, hence the name black hole. What is truly fascinating about black holes is their event horizon. This is a boundary surrounding the black hole, beyond which nothing can return once crossed. The event horizon can be envisioned as the point of no return. Anything that crosses this boundary is pulled inexorably toward the singularity, which is the core of the black hole, where gravity is thought to be infinitely intense in space as we understand it ceases to exist. Interestingly, black holes can also form through other processes, such as a merging of neutron stars, or through the gradual accumulation of matter around a supermassive black hole at the center of galaxies. These supermassive black holes can have millions or even billions of times the mass of our Sun, illustrating the astonishing variety of cosmic phenomena resulting from the life and death of stars. Black holes represent one of the most enigmatic and fascinating areas of astrophysics, where gravity becomes so intense that even light cannot escape. Among the most compelling theories surrounding black holes is the idea that they warp space-time dramatically. According to Albert Einstein's general theory of relativity, massive objects like stars and planets curve the fabric of space-time around them. In the case of black holes, this curvature is extreme, creating what can be visualized as a funnel or well in the space around them. As matter spirals into a black hole, it is believed to form an accretion disk, heating up to enormous temperatures and producing powerful radiation, including X-rays. This phenomenon not only affects the immediate vicinity of the black hole, but can also impact nearby stars and entire galaxies, pulling them closer and altering their paths. The interaction of black holes with their surroundings can stir the galactic pot, leading to the formation of new stars, or even initiating explosive phenomena like gamma-ray bursts. Another intriguing theory stems from the concept of singularities at the core of a black hole, where density becomes infinite. The known laws of physics cease to function as we understand them. This suggests that black holes might hold the key to new physics, possibly reconciling the theories of quantum mechanics and relativity. Some scientists propose that within these singularities, the fabric of space-time may be so distorted that it could create routes to other regions of the universe, or even parallel universes. The phenomenon of Hawking radiation, proposed by physicist Stephen Hawking, introduces a further layer of complexity. It suggests that black holes can slowly evaporate over time through the emission of radiation due to quantum effects near the event horizon. This discovery implies that black holes are dynamic objects that might not be eternal, but instead undergo changes, challenging our long-held perceptions of them as immutable cosmic giants. Through these theories, black holes continue to captivate and challenge our understanding of the universe, encouraging scientists to explore the profound mysteries of gravity, energy, and the fundamental structure of reality itself. Black holes may be invisible, but astronomers have developed ingenious methods to infer their presence and study their properties. The key lies in the way black holes interact with their surroundings. When a massive star collapses, it forms a black hole that possesses an incredibly strong gravitational pull, which can attract nearby gas and dust. As this matter spirals towards a black hole, it heats up to extreme temperatures and emits intense radiation, particularly in the form of X-rays. This radiation is what allows us to detect the presence of a black hole, often revealing itself in breathtaking bursts of energy. Observations often focus on the effects of gravity on nearby stars. When scientists notice a star orbiting around an invisible object, they can deduce the mass of that object by observing the star's motion. If the mass is extraordinarily large and no light can escape from the center, it suggests the presence of a black hole. This technique became important in the late 20th century when the supermassive black hole at the heart of our own Milky Way galaxy, known as Sagittarius A star, was identified through the orbits of surrounding stars. Another groundbreaking method emerged with the Event Horizon Telescope, a network of radio observatories around the globe. In 2019, this collaboration took a remarkable leap forward, capturing the first image of the event horizon, or the boundary beyond which nothing can escape a black hole. This image showed a glowing ring of light around a completely dark center, providing visual evidence of a black hole's existence and offering profound insight into their structure. Through these observations, scientists have gained valuable information about the size, spin, and other properties of black holes. While they may remain invisible in a traditional sense, our understanding of them has grown tremendously, thanks to a combination of creative technologies and careful observation of the universe around them. Thus, the seemingly unreachable mysteries of black holes continue to be unraveled, leaving us in awe of their powerful nature. Recent discoveries about supermassive black holes have deepened our understanding of these enigmatic giants that reside at the hearts of most galaxies. Astronomers have established that virtually every large galaxy contains one of these black holes, which can possess masses millions to billions of times greater than that of our Sun. Observations, using advanced telescopes, including those that detect radio waves and infrared light, have unveiled the mechanisms through which these colossal entities influence galaxy formation and evolution. One of the groundbreaking findings indicates a possible connection between supermassive black holes and star formation rates in their host galaxies. It appears that as these black holes grow, they can emit powerful jets of energy known as relativistic jets that travel vast distances across space. This interaction can regulate the amount of gas available for star formation, effectively quenching it in the vicinity. Such a feedback loop suggests that the black hole's growth is intricately linked to the evolution of the galaxy itself, challenging prior assumptions about their roles. Moreover, observational advancements, especially with instruments like the Event Horizon Telescope, have provided unprecedented images of the shadow cast by a black hole's event horizon. In a landmark achievement, astronomers captured the shadow of the supermassive black hole in the galaxy M87, allowing scientists to study the physics of black holes in real time, something that had only been theorized before. This observation not only showcased the existence of these powerful entities, but also offered insights into how black holes accrete matter and the behavior of surrounding material. Additionally, the galactic mergers of the past have brought to light new possibilities for understanding the dynamics of supermassive black holes. When two galaxies collide, their central black holes may merge as well, creating a larger black hole. This event has implications for the gravitational waves detected by facilities like the Laser Interferometer Gravitational Wave Observatory. Such discoveries illuminate not only the dark nature of black holes, but also the shaping forces they exert on the universe itself, making these findings crucial to our understanding of cosmic evolution. Dark matter is an enigmatic substance that permeates the universe, making up approximately 27% of its total mass and energy content. Despite its name, it does not emit, absorb, or reflect light, which is why it remains invisible to our current detection methods. The existence of dark matter was first inferred through the gravitational effects it has on visible matter, such as galaxies and galaxy clusters. For instance, when astronomers observe how galaxies spin, the speed of their rotation suggests that there is much more mass present than what we can see. This unseen mass is attributed to dark matter. Astronomical observations, particularly the study of galaxy rotation curves and cosmic microwave background radiation, reveal that dark matter acts as a cosmic scaffold. It provides a gravitational glue that holds galaxies together and affects the formation of large-scale structures in the universe. Without it, the universe as we know it would be a dramatically different place. The behavior of galaxies indicates that they contain far more mass than the stars and gases we can directly observe, evidencing dark matter's critical role in shaping cosmic formations. The search for the nature of dark matter is one of the most intriguing quests in modern astrophysics. Numerous theories have been proposed, ranging from exotic particles like weakly interacting massive particles to modifications of gravitational theories. While experiments are continuously being conducted to detect dark matter directly, its elusive nature has made it a persistent mystery. Not only does it challenge our understanding of the universe, but it also pushes the boundaries of particle physics and cosmology. Understanding dark matter is essential for unraveling the history of our universe and predicting its eventual fate. It plays a key role in the evolution of galaxies and clusters, impacting how they interact and evolve over billions of years. As scientists work to unveil the properties and components of dark matter, they unlock deeper insights into the very fabric of reality, leading to an enriched understanding of what we are made of in the universe that surrounds us. To uncover the elusive nature of dark matter, scientists employ a variety of inventive methods. Relying on gravitational effects, the vast majority of matter in the universe, which comprises galaxies and clusters of galaxies, acts in ways that suggest there is far more mass present than what can be seen. For instance, when astronomers observe the motion of stars within a galaxy, they find that the stars at the outer edges are moving much faster than expected. This discrepancy indicates that there is significant unseen mass, often attributed to dark matter, influencing their motion. Gravitational lensing is another fascinating technique used to detect dark matter. When massive objects like galaxy clusters sit between us and a more distant object, their gravitational field can warp space itself. This distorts the light from background galaxies, causing them to appear stretched or magnified. By analyzing these lensing patterns, scientists can map out the distribution of mass, including dark matter, within those intervening galaxy clusters. This allows researchers to draw conclusions about the dark matter's presence, even though it does not interact with light. Additionally, scientists study the cosmic microwave background radiation, which is the afterglow of the Big Bang. Variations in temperature and density within this ancient radiation give clues about how matter, including dark matter, influence the structure of the universe. By comparing observations of the cosmic microwave background to theoretical models, researchers can infer the amount and distribution of dark matter in the early universe and understand its role in cosmic evolution. Finally, particle physics experiments, such as those conducted in underground laboratories, seek to directly detect dark matter particles. Scientists look for rare interactions between these proposed dark matter particles and regular matter. If dark matter is composed of particles, as many theories suggest, finding them will provide direct evidence of its existence. While direct detection has yet to yield conclusive results, these ongoing efforts exemplify scientists' commitment to unlocking the mysteries of dark matter, a substance that constitutes a substantial portion of the universe, yet remains hidden from our current observational tools. Dark matter remains one of the most enigmatic components of our universe, eluding direct detection, and yet accounting for approximately 27% of its total mass and energy content. Among the leading hypotheses is the existence of weakly interacting massive particles, commonly referred to as WIMPs. These hypothetical particles would interact through the weak nuclear force, allowing them to pass through ordinary matter almost unnoticed, much like neutrinos do. If these particles exist, they could potentially be detected in experiments designed to capture their faint interactions with regular matter. Another intriguing candidate for dark matter consists of actions, which are tiny light particles proposed to resolve certain problems in particle physics, such as a strong CP problem. These particles would be extremely light and abundant in the universe. Like WIMPs, actions are challenging to detect directly, but specific experimental setups aim to catch their signatures. The theoretical framework surrounding actions is fascinating, as their existence could bridge gaps in our understanding of fundamental forces. Primordial black holes also present a compelling possibility for dark matter constituents. These objects could have formed in the very early universe due to density fluctuations, emerging before stars and galaxies. With masses that vary widely, they could account for dark matter, especially if they were created in sufficient abundance. Ongoing research is investigating whether these elusive black holes might be revealing their presence through gravitational effects on surrounding matter. In addition, some researchers are exploring modified theories of gravity as an alternative explanation, proposing that our current understanding of gravitational dynamics may need adjustment to account for observations attributed to dark matter. As scientists continue their quest to unveil the nature of dark matter, these hypotheses serve as tantalizing leads in a universe filled with mysteries waiting to be unraveled. Dark matter is an elusive yet crucial component of our universe, playing a significant role in the formation and movement of galaxies. Although it cannot be seen or detected directly, scientists infer its presence through its gravitational effects. Dark matter makes up about 26% of the total mass-energy content of the universe, while only about 5% corresponds to the ordinary matter that forms stars, planets, and other celestial bodies. In the early stages of the universe, just after the Big Bang, ordinary matter was scattered uniformly. However, it was a gravitational pull of dark matter that began to shape the cosmos. Clumps of dark matter formed due to slight fluctuations in density. These clumps provided the gravitational wells that attracted and concentrated ordinary matter, leading to the formation of the first galaxies. Galaxies would likely never have undergone the same complex processes of coalescence that we observe today. Once galaxies formed, dark matter continued to influence their dynamics. As galaxies move through space, they are not only interacting with each other, but are also seated in halos of dark matter. This dark matter halo contains far more mass than the galaxies themselves and exerts a gravitational influence that keeps galaxies bound together and regulates their rotation. Observations show that stars on the outskirts of galaxies move at speeds that cannot be accounted for by the visible matter alone. This discrepancy is a key piece of evidence for dark matter, suggesting that these galaxies are embedded in vast, unseen structures. Moreover, dark matter helps shape the large-scale structure of the universe. It is thought to guide the distribution of galaxies into clusters and filaments, creating a web-like structure throughout space. This interconnected framework, largely composed of dark matter, supports the visible galaxies while also affecting their trajectories and interactions. Consequently, dark matter is not just a mysterious backdrop. It is a fundamental player in the choreography of cosmic evolution, governing the dance of galaxies across the vast expanse of the universe. The universe is a tapestry woven from known and unknown forces, and at its heart lies the mystery of dark matter, which may hold the key to understanding several gravitational anomalies. When astronomers observe galaxies, they note that stars in the outer regions rotate around the center at speeds that defy the gravitational pull of the visible mass. This creates a conundrum. The amount of mass that can be seen does not account for the speeds being witnessed. The solution that many scientists propose is the existence of dark matter. Dark matter is a peculiar form of matter that does not emit, absorb, or reflect light, making it invisible to telescopes. Its existence is inferred through its gravitational influence on visible matter, such as stars and galaxies. It is believed to make up about 27% of the universe. The presence of this unseen mass explains why galaxies can hold on to their outer stars, even though the visible matter alone cannot provide sufficient gravitational force. Dark matter acts as a cosmic scaffold that supports the structure of galaxies. Moreover, dark matter plays a significant role in the formation of large-scale structures in the universe, like galaxy clusters. Observations of the cosmic microwave background radiation, the afterglow of the Big Bang, also suggest that dark matter contributed to the formation of clumps that later resulted in galaxies and other celestial bodies. Without dark matter, the distribution of galaxies would look very different than what we observe. Today, not only does dark matter help clarify the rotational speeds of galaxies, but it also addresses other gravitational anomalies, such as gravitational lensing. This phenomenon occurs when massive objects, like galaxy clusters, bend the light from objects behind them, an effect that dark matter amplifies. While dark matter remains elusive, its role in cosmology continues to intrigue scientists. As observational techniques improve, new insights into dark matter's nature and influence may reveal even more about the fabric of our universe. There have been intriguing observations in the cosmos where galaxies appear to vanish, leading astronomers to question what might be happening in the vast universe. One notable case involved a galaxy known as GVB 1800. This galaxy was initially detected in the data from the Cosmic Evolution Survey. It seemed to sparkle brightly, drawing the attention of researchers. However, when astronomers aimed deeper observations, the galaxy was nowhere to be found, leading to speculation about its true nature and what could cause such a phenomenon. Another fascinating case emerged from early observations of the Hubble Space Telescope. Astronomers noted several distant massive galaxies at a time. Some of these galaxies, thought to be thriving in their formation, unexpectedly faded from view in subsequent studies. This behavior perplexed scientists. The prevailing hypothesis is that these missing galaxies may have suffered from significant cosmic events, like mergers, where they combine with other galaxies, leading to their light being redistributed or diminished rather than fully disappearing. There could also be cases where the light from these galaxies is obscured by intervening cosmic dust or gas, which can absorb or scatter light, making them effectively vanish from our viewpoint. This phenomenon has been especially difficult to unravel in the early universe, where dense regions of gas and dust were much more common. Such complexities remind us how dynamic and changing the cosmos is, shaping our understanding of galaxy formation and evolution. Furthermore, researchers are honing their detection methods with advanced technology, discovering how elusive these galaxies can truly be. With each new survey and observation, our grasp of the nature of these celestial bodies expands. But questions persist. What might we uncover about the evolution of the universe when we finally decode the tales these missing galaxies have to tell? The quest to find the secrets of these vanished galaxies continues, keeping astronomers both challenged and inspired. Disappearing galaxies present a fascinating puzzle in the realm of cosmology. In the vastness of the universe, we observe many galaxies that seem to fade or vanish from our view over time. This phenomenon can be attributed to several intricate factors, primarily involving the concepts of cosmic expansion, dark matter, and the limits of our observational techniques. One significant aspect contributing to this disappearing act is the ever-expanding nature of the universe. Galaxies are moving away from each other as a result of this expansion, propelled by a mysterious force that we call dark energy. When galaxies drift further away from us, their light becomes increasingly redshifted, meaning that it is stretched to longer wavelengths. Eventually, some galaxies may transition beyond the threshold where their light can reach us, causing them to appear to disappear from our observations. Additionally, the role of dark matter cannot be underestimated. Dark matter, which is invisible and interacts primarily through gravity, makes up a significant portion of the universe's total mass. It influences the formation and distribution of galaxies. In instances where galaxies are primarily composed of dark matter, their interactions and the gravitational effects from surrounding fields may lead to complex behaviors, making them harder to detect. Finally, there are limitations concerning our observational capabilities. Telescopes, no matter how powerful, can only detect a certain amount of light, and as galaxies become more distant, faint, or obscured by intergalactic dust and gas, they become challenging to identify. As we look deeper into the universe, we may encounter countless galaxies whose light is simply too weak for our current technology to capture. The phenomenon of disappearing galaxies ultimately highlights the dynamic and ever-changing nature of the cosmos. Each vanished galaxy adds to our understanding of the universe's complexity and beckons science to refine their models and observational techniques. As our technology continues to advance, there is hope that we will unveil even more secrets the universe has yet to reveal. The existence of disappearing galaxies presents profound implications for our understanding of time and space. When we observe galaxies that seem to fade away or become less detectable, it challenges a conventional idea that the cosmos is a static entity. Instead, it suggests a dynamic universe in which even massive systems can undergo dramatic changes, thus redefining our perspective on how we perceive both time and the vastness of space. As we delve deeper into this phenomenon, we must consider how time plays a role in the life cycle of galaxies. Galaxies, much like other celestial bodies, evolve over billions of years. Their disappearance could stem from several factors, including the gravitational influence of neighboring objects, the consumption of their stars through various processes, or the effects of dark energy driving the accelerated expansion of the universe. This revelation prompts us to rethink the concept of time itself. Rather than being a simple linear progression, time may interact intricately with cosmic events, leading to the gradual fading of entire galaxies. Space, too, is affected by this phenomenon. The notion of vast distances separating celestial objects takes on new meaning when some of those objects can seemingly vanish from our view. This prompts us to question what we consider to be an occupied space. If galaxies can disappear due to being too distant or obscured by cosmic dust, then the spatial framework we use to understand the universe becomes more complex. It signals that there are areas of the cosmos that are in an ever-changing state of flux, highlighting the transient nature of what we observe around us. Furthermore, the implications of disappearing galaxies may extend our understanding of cosmic evolution. They could serve as indicators of unseen processes at work, revealing the complexities of galaxy formation, interaction, and disappearance. This leads not only to an enriched understanding of astronomy, but challenges scientists to consider broader, more intricate models of cosmology. In this sense, the disappearing galaxies become not just elusive objects in space, but vital clues that reshape our conception of the universe and our place within it. The phenomenon of disappearing galaxies is indeed an intriguing topic, and discussions in the realm of cosmology suggest a potential connection to dark energy, a mysterious force that permeates the universe. As galaxies move apart over time due to the universe's expansion, dark energy plays a significant role in accelerating this expansion. It influences not only the expansion itself, but may also affect the visibility of galaxies over vast cosmic distances. Theories propose that as galaxies recede beyond a certain threshold, they could become less detectable to our telescopes, potentially due to the redshift effect. Redshift occurs because, as light travels through expanding space, its wavelength stretches, shifting it towards the red end of the spectrum. This can mean that galaxies which were once bright and clear could fade from view, effectively disappearing from our perspective. When a galaxy's light shifts beyond the range we can observe, it may seem to vanish. Additionally, dark energy could indirectly impact the formation and evolution of galaxies. It might influence the clustering of matter, leading to a scenario where some galaxies are pushed away from our observable universe. This could contribute to the idea that certain galaxies, instead of being lost forever, are merely hidden from us in a part of the universe that expands faster than we can track. Yet, this interplay of dark energy and the disappearing galaxies is still an area of active research. Scientists are studying the complex gravitational dynamics at play and how they interact with the fabric of space-time. As we continue to explore these fascinating interactions, our understanding of the universe's structure will deepen, revealing more about the elusive nature of dark energy and its impact on the galaxies we observe. The study of disappearing galaxies offers fascinating insights into the long-term fate of our universe. Observations have revealed that a number of galaxies appear to be vanishing from view due to various factors, such as cosmic interactions or the influence of dark matter. As we investigate these phenomena, it becomes clear that galaxies do not exist in isolation. Rather, they are dynamic systems influenced by their surroundings and by the vast interconnected web of cosmic forces. One of the most striking factors in the disappearance of galaxies is a phenomenon known as galactic cannibalism. Larger galaxies can exert gravitational forces that draw in and consume smaller galaxies. This process not only alters the structure and composition of the larger galaxy, but can also lead to the gradual fading of the smaller galaxy's distinct features, effectively erasing it from our observational landscape. Understanding this dynamic reshapes our perception of cosmic evolution, illustrating how galaxies are not just static entities but participants in a relentless cosmic dance of birth, death, and transformation. Additionally, the study of disappearing galaxies challenges our understanding of dark energy, which is believed to be driving the accelerated expansion of the universe. As galaxies recede from each other due to this expansion, some will become unreachable, leaving only the most massive and brightest galaxies to dominate our observable universe. This shift in view prompts us to ponder, what will our universe look like in billions of years? These insights remind us that the universe is a constantly evolving tapestry where interactions and transformations determine the fate of galaxies. Each new discovery about these disappearing galaxies can reshape our expectations of cosmic history and future, compelling us to question whether the grand narrative of the universe is one of perpetual growth and complexity, or if it ultimately leans toward decline and solitude. The theory of relativity, formulated by Albert Einstein, reveals a fascinating interplay between time and gravity, fundamentally changing our understanding of the universe. According to this groundbreaking theory, time is not a fixed entity but can stretch and contract based on gravitational fields. This means that the stronger the gravitational pull, the slower time moves. This concept is known as gravitational time dilation. To illustrate this, consider two observers, one located on Earth and another in a spacecraft far from any massive objects. The observer on Earth, feeling the effects of our planet's gravity, experiences time more slowly than their counterpart in space. This is not just theoretical, it has practical implications. Precision experiments, often involving atomic clocks, have demonstrated that clocks located at different altitudes, one on the ground and one on a mountain, actually tick at slightly different rates. The clock at the higher altitude, experiencing weaker gravity, ticks faster than the one on the ground. This relationship has profound implications for our understanding of the cosmos. It suggests that time is flexible and influenced by factors we might have considered unrelated, like the mass of an object. As a result, the more massive an object, as with planets and stars, the more significant the effect it has on the passage of time. This means that time near a black hole, for instance, would slow down dramatically compared to time experienced far away from such dense objects. Einstein's insights lead us to reconsider notions of simultaneity and the flow of time itself, emphasizing how interconnected gravity and time truly are. These perspectives shape our understanding of cosmic events, from the behavior of neutron stars to the very fabric of space-time, enticing astronomers and physicists to delve deeper into these remarkable connections. When we discuss the extraordinary effects of time near large celestial bodies, particularly black holes, we delve into an intriguing aspect of Einstein's theory of general relativity. This theory reveals that massive objects can warp the fabric of space-time around them. As a result, time behaves differently depending on your proximity to these immense gravitational wells. For someone standing far away from a black hole, time would appear to flow normally. However, for an observer who ventures too close, the experience shifts dramatically. As they approach the event horizon, the point of no return surrounding a black hole, time will seem to slow down relative to the outside observer. To someone watching from a distance, the infalling observer would appear to move in slow motion as they approach that crucial boundary. In fact, just before crossing the event horizon, they might even appear to freeze in place, becoming increasingly redshifted until they vanish from view. This phenomenon is not merely theoretical. It also poses fascinating possibilities for both scientific exploration and science fiction narratives. If, hypothetically, one could traverse the event horizon and survive the experience, the journey would allow them to reach a point where they age more slowly than those who remain far from a black hole. While the details of such an experience remain speculative, the implications ignite our imagination regarding time travel and the nature of reality itself. In the universe's grand tapestry, this warp in the flow of time reveals layers of cosmic intricacy, challenging our perception of the past, present, and future. As researchers continue to study the effect around black holes, the quest to understand time itself carries us further into a realm where science and wonder intersect. Time travel, a concept both alluring and perplexing, has inspired numerous thought experiments that delve into its intriguing complexities, particularly concerning time distortion. One of the most famous is known as the twin paradox. Envision a scenario where one twin embarks on a journey into space at a speed nearing that of light, while the other remains on Earth. Upon the space-traveling twins' return, they would find that they have aged much less than their Earth-bound sibling. This fascinating disparity arises from the effects of time dilation, where time itself slows down for objects moving at significant fractions of the speed of light. This thought experiment not only illustrates the strange relationship between speed and time, but also challenges our perceptions of aging and reality. Another well-known paradox is the grandfather paradox. Imagine a time traveler venturing back in time to a period before their grandfather met their grandmother and inadvertently preventing their grandfather from ever having children. If this were to occur, the time traveler wouldn't exist to undertake the journey in the first place. This perplexing scenario raises deep philosophical questions about causality and the nature of time itself, sparking debates on whether timelines can diverge, merge, or even erase themselves. The grandfather paradox invites contemplation about the rules that govern time travel, revealing that our understanding of time is not merely linear. The bootstrap paradox further complicates the narrative of time travel. This paradox suggests a situation in which an object's existence is both a result and the cause of a time loop. For instance, if a time traveler were to go back in time and hand Shakespeare a copy of his own works, who is the true author? The question becomes a riddle of origins, illustrating how time travel could blur the lines between past and future. This thought experiment challenges our understanding of authorship and creativity, suggesting that events in time may not be as straightforward as they seem. Lastly, consider the concept of a closed time-like curve. In certain solutions to Einstein's equations of general relativity, a path through space-time can loop back on itself, creating a time travel scenario where one could revisit the past. This theoretical possibility hints at strange implications for time and existence. Such curves lead to questions about whether free will can coexist with predestined events, and how choices might alternate or converge across different timelines. Each of these thought experiments pushes the boundaries of our comprehension of time, leaving us in awe of the myriad possibilities that stem from the concept of time travel. Recent experiments have delved into profound implications of time distortions, particularly as they relate to the fabric of our universe. One notable area of exploration involves the effects of extreme gravitational fields, as predicted by the theory of general relativity. High-precision atomic clocks have been utilized to measure time variations at different elevations. These experiments illustrate how time passes more slowly in stronger gravitational fields, as observed when comparing clocks positioned at sea level to those located on the summit of high mountains. In addition to experiments on Earth, researchers have taken to the skies and beyond. For instance, scientists aboard airplanes have conducted experiments where atomic clocks have flown at high speeds, comparing their time with identical clocks left on the ground. These high-speed experiments have confirmed that time dilates or stretches as an object approaches the speed of light in accordance with Einstein's equations. The results from these flights serve as a tangible demonstration of how rapidly moving objects can experience time differently than stationary ones. Known as muons, provide additional insights into time distortions. Created from cosmic rays interacting with Earth's atmosphere, muons are unstable and decay quickly. Yet, when scientists accelerate them close to the speed of light in particle accelerators, they observe that these muons last much longer than they do at rest. This phenomenon is yet another manifestation of time dilation, reinforcing the reality of time's malleability, but also opening doors to new technologies like more accurate global positioning systems. As researchers continue to test the boundaries of time, they enhance our comprehension of the universe and our dance between speed, gravity, and the relentless march of time. Time distortions have profound implications for our understanding of the cosmic timeline. When we refer to time distortions, we are primarily talking about effects that arise from Einstein's theory of relativity. Light from those objects takes years, sometimes even millions or billions of years, to reach us. While that light is traveling, the objects themselves may be experiencing time differently. For instance, a spaceship traveling close to the speed of light would age much slower compared to people on Earth. This phenomenon, known as time dilation, can cause significant discrepancies in our understanding of the timing of events in the universe. If we were to study an object that is moving rapidly through the cosmos, we might interpret its current state based on the light we receive, but that state may not accurately reflect where the object is in its own timeline. Moreover, gravitational time dilation adds another layer of complexity to our cosmic timeline. In regions of strong gravitational force, such as near black holes, time can flow more slowly relative to areas of weaker gravitational fields. This means that, theoretically, if we were to observe phenomena near a black hole, we would perceive those events occurring much more slowly than they do from the perspective of a distant observer. This could lead to misunderstandings about the rate at which certain cosmic processes occur, further complicating our ability to piece together the history of the universe. Ultimately, these time distortions challenge our conventional understanding of history as a linear progression. Far from being a simple timeline of events, the cosmos may instead present us with a tapestry woven together by different rates of time experience in various locations and circumstances. Understanding these distortions is crucial if we aspire to comprehend the grand narrative of the universe, including the formation of galaxies, the life cycles of stars, and the very essence of cosmic evolution. The concept of parallel universes opens up a whole new frontier in our understanding of reality. Picture a vast tapestry of existence, where each thread represents a different version of our universe, each functioning independently but sharing certain fundamental traits. This notion emerges from various fields of science, including physics and cosmology, and suggests that there could be countless realities coexisting alongside our own. At the heart of this idea is the interpretation of quantum mechanics, particularly the many worlds interpretation, which posits that every time a decision is made or an event occurs with multiple potential outcomes, the universe splits, creating a new, separate reality for each possibility. This means that for every choice we make, a different version of ourselves may be living out an alternate outcome in another universe. Such a concept dramatically reshapes our understanding of cause and effect, fate, and free will. Additionally, the theory of cosmic inflation proposes that during the very early moments of the universe, rapid expansion created regions of space that developed into separate bubbles, each potentially having different physical laws and constants. These bubbles can serve as their own universes, leading to the idea of a multiverse, a term used to describe this collection of universes. This challenges not only our perception of the universe, but also confronts philosophical inquiries regarding our existence and the nature of reality itself. As we delve deeper into the implications of parallel universes, we start to confront profound questions about the nature of existence, identity, and the limits of our knowledge. Are we truly alone in our experiences, or are there countless versions of ourselves exploring different paths in unimaginable realities? These are ideas, while speculative and challenging to comprehend, invite us to explore beyond the known and question the very fabric of what we consider reality. Quantum mechanics delves into the strange behavior of particles at the smallest scales, and some interpretations of its principles suggest the existence of parallel universes. One of the most well-known theories is the many worlds interpretation proposed by physicist Hugh Everett III in 1957. According to this idea, every time a quantum event occurs with multiple possible outcomes, the universe splits into different branches. Each outcome manifests in a separate, parallel universe, creating a vast multiverse where every possible scenario plays out. Entanglement also hints at this concept. When two particles become entangled, the state of one instantaneously affects the state of another, regardless of the distance separating them. This interconnectedness raises questions about the nature of reality. Some scientists speculate that our universe could be just one of many, where various outcomes have occurred based on the entangled states of particles. This notion challenges our understanding of singular existence and promotes the idea that multiple realities could coexist simultaneously. Another fascinating theory is quantum decoherence, which sheds light on how classical reality emerges from quantum mechanics. In this framework, as quantum systems interact with their environments, they lose their ability to exhibit superposition, that strange state where particles can be in multiple positions at once. This process of decoherence effectively explains why we do not see these quantum effects in our everyday lives. Yet it implies that all those potential states could correspond to different universes. Finally, string theory, which attempt to unify all fundamental forces of nature, also hints at a multiverse. In string theory, the complexity of dimensions and the different ways strings can vibrate could lead to the existence of many separate universes, each with its own unique physical laws and constants. This approach intertwines with the concept of parallel universes, suggesting a richly layered reality where countless variations of existence emerge from the underlying fabric of the cosmos. The multiverse theory offers a compelling framework for understanding some of the peculiarities observed in our universe. At its core, this theory posits that our universe is just one of many, possibly an infinite number, each with its own set of physical laws and constants. This broad spectrum of universes could help clarify why certain cosmic phenomena seem anomalous or difficult to reconcile with our current understanding of physics. Take, for instance, the unusual distribution of galaxies across the cosmos. Our universe exhibits regions where galaxies are oddly sparse or clumped together in ways that don't quite align with predictions made by traditional cosmological models. The multiverse theory suggests that these discrepancies might stem from our universe being one of many, each emerging from different initial conditions. In this context, it's not surprising to find distinct patterns or anomalies arising due to variations in the laws of physics among the different universes. Additionally, the multiverse theory provides a framework for understanding cosmic inflation, a period of exponential expansion in the early universe. According to this theory, the multiverse can produce bubble universes that each experience different inflationary scenarios. Some bubbles might expand rapidly, while others may experience slower rates of inflation, leading to diverse universes with unique properties. These variations can result in phenomena such as dark energy behaving differently in different regions of space, potentially shedding light on why our dark energy appears to accelerate cosmic expansion. Furthermore, certain cosmic mysteries like dark matter and dark energy might find more straightforward explanations within a multiverse context. If there are universes with distinct properties, some might exhibit forms of matter or energy that are not present in our own universe. This could clarify why we observe certain effects without fully understanding their origins. By considering a broader landscape of potential realities, the multiverse theory not only addresses specific anomalies but also invites us to rethink our position in the cosmos. The concept of parallel universes introduces a profound shift in how we think about fate and determinism. In a multiverse scenario, where countless universes exist simultaneously, each with its own set of circumstances, the traditional view of a singular fate begins to unravel. If every possible outcome is realized in one universe or another, then the notion that our paths are predetermined becomes less compelling. For instance, consider a decision that seems significant. In one universe, you might choose to take a job in a new city, while in another, you could decide to stay in your current role. Each choice leads to different life experiences, suggesting that fate is not a fixed path but a vast landscape of possibility. This framework challenges a deterministic perspective, which posits that every event is the inevitable result of preceding events. If multiple versions of reality exist based on different choices, it opens a door for a more nuanced understanding of cause and effect across various realities. Furthermore, this idea also touches upon the nature of individual agency. In a multiverse filled with countless cells making distinct choices, our sense of control over our destinies might seem diluted. Yet, it raises an intriguing philosophical question. If we can only experience one version of our lives, does it matter whether our choices are part of a larger web of possibilities? The implications extend to moral responsibility as well. If our actions could lead to entirely different outcomes in alternate realities, how do we judge what is right or wrong within our singular life context? The existence of parallel universes invites us to reconsider fundamental questions about our existence, the nature of choice, and the essence of what it means to be human. It presents a universe rich with potential, prompting us to explore how our understanding of reality shapes the lives we lead and the decisions we make. The concept of crossing paths with another universe delves into the realms of theoretical physics and cosmology, where ideas often push the boundaries of what we know. One intriguing perspective comes from the multiverse theory, which suggests that our universe might be just one of countless others, each with its own set of physical laws and constants. Some scientists propose that interactions between these universes could influence conditions in our own, possibly providing evidence of their existence. Certain phenomena in our universe, such as cosmic microwave background radiation irregularities, have led some researchers to speculate about the potential influence of parallel universes. For instance, some anomalies may hint at collisions with other universes, creating ripples in space-time that we could detect. However, these interpretations remain speculative, as the tools we possess today may not yet be refined enough to conclusively demonstrate a multiverse interaction. Another fascinating area of inquiry lies in the study of black holes. Some scientists hypothesize that black holes could act as gateways to other universes. If this notion holds weight, then understanding the nature of black holes could unlock secrets not merely of our universe, but the existence of others, hinting at a shared cosmic tapestry that we have yet to fully comprehend. While currently, there exists no direct evidence proving that we have intersected with another universe, the ideas surrounding this topic invite fascinating discussions and ongoing research. The pursuit to uncover the mysteries of our cosmos might eventually reveal hints pointing to other universes, allowing us to explore dimensions of existence beyond our own.